In this video we will take a look at optimization. What is it? It is a way to make your program or game run faster. I want to give you some common techniques that can really boost your program's performance. The rule of thumb here is to know what you need to optimize. So you can use a profiler to measure what parts of your program are slow. Here are those techniques that I'm about to explain. They can make your game run maybe 5, maybe 10, maybe 100 times faster, who knows? But let's actually split them into two parts. Techniques that apply on CPU or central processing unit, and techniques that apply on GPU or graphics processing unit. But before we move forward, I want you to take a look at this graph. It shows us that over the last decades, the performance of processors has grown much faster than the performance of memory, or RAM if you will. For us it means that even if you are able to write fast code, this code will be slow if you don't know how to write data-friendly code. How to do that? Well, everything I can say is know your data. For example, let's say we have this image and we want to invert its colors. Implementation of the algorithm may look something like that. Here we have a loop inside a loop to iterate over horizontal and vertical pixels. Then we get the color of the pixel located at x and y coordinate, invert it, and finally store it into the resulting image. Pretty simple, isn't it? Yeah, pretty simple and horribly slow. Well, what if I tell you that just by changing the way we index our loops, we can speed up this algorithm 5 times or more? It depends on the size of the image. You can ask, why? I don't believe it. To understand that, we need to understand the basics of how cache works. Here are our CPU and the main memory. When we want to access a pixel of our image, a CPU initiates instruction to fetch some bytes from our memory. However, the cost of that fetch is very high, something about hundreds of CPU cycles. Just for comparison, the whole routine of inverting a pixel's color may take 10 to 15 cycles. I want you to take a moment, guys, to appreciate how smart hardware manufacturers are. They put an additional small magic memory thing called cache into here. The purpose of the cache is to save some data that is being requested from the main RAM. It is placed on the CPU really near the chip, and so the cost of accessing that memory is really small. Actually, modern computers have from 2 to 4 caches. They are called L1, L2, L3 and so on. The higher the number, the further they are placed from CPU, the greater their size, as well as the cost of access. But for simplicity, let's say that we'll have just a single cache. So when we try to access a pixel, we first check if it has already been placed in cache. If not, we must wait hundreds of CPU cycles to finish fetching that memory from main RAM. This situation is known as cache miss. The cost of it is very high, as you already see. After that, the data that we fetched is placed into the cache. And finally, we now have our pixel that we can use and modify in the application. Next time, when we try to fetch that same pixel, the CPU initiates the fetch, checks whether or not it exists in the cache. This time it exists there, and we don't need to waste so much precious time. This situation is known as a cache hit, and that's good. The more cache hits we have, the better. We can't avoid cache misses completely, but we can organize and use our data so that we have less cache misses and more cache hits. What is a cache? It's basically just a bunch of memory. But the interesting thing here is that the data is placed into the cache as contiguous blocks called cache lines. Usually they have size of 64 bytes. If a cache line hasn't been used for a while and there's new data to insert, the cache line can be overwritten, which is known as cache line eviction. But enough theory for now, let's return back to our image example. Usually, images are stored in memory as rows of pixels, left to right, top to bottom. What does it mean for us? When we walk through our pixels as rows, we read a pixel. If it wasn't in cache, the memory controller will fill the 64-byte cache line with memory that is placed at that address. So the next pixels will already exist in the cache and access to them will be very fast. In fact, this situation when nearby addresses are more likely to be in the cache is known as data locality. But remember, our first implementation walked through pixels as columns. That way, each first pixel in a column will cause a cache miss, and probably when we will reach the next column, the data for the pixel will already be evicted from the cache. It will cause lots and lots of cache misses, and not surprisingly, the execution will slow down a lot. Remember guys, always know your data. Modern cache systems are really smart and do a lot of things to minimize cache misses. However, they are far beyond the scope of this video. You can read more about them in the Game Engine Architecture book. But for now, let's move forward. Imagine we have a cubic pig in our game. It can have position, velocity, health, hunger, and maybe some other components. Let's say this data takes 64 bytes of information to store, so that it will fully occupy one cache line. Now imagine that we have an array of 64 of these pigs, and we want to update their positions. In memory they will look something like that, one pig per cache line. Notice that to fetch a position for pig, we are guaranteed to do a cache miss, so looping over many pigs will be very slow. Or I should say, slower than it possibly can. This approach of holding objects in memory is known as array of structures. But imagine that instead of this, we'll have a structure that will hold arrays of the same object's attributes, positions, velocities, and so on. When we try to fetch a first position, we'll face one cache miss. But then positions of the next 5 pigs will be placed in the cache line as well. That way we can expect a cache miss once per 5 positions, instead of once per position. General advice is try to keep properties of your objects as in arrays where possible. That approach is known as structure of arrays, because we literally store arrays in a structure. And that is great! This situation is an interesting example of data locality. I can give my personal example. When I tried to optimize Rubik's Cube, I managed to make Cubist calculations 2 times faster just by changing the way how transfer matrices are laid out in memory. Awesome! SIMD stands for Single Instruction Multiple Data. It's basically just a set of instructions that allow you to combine the same operations on multiple data elements into one instruction. You can multiply 4 integers, divide 4 floats, shift, and, or take square root without any additional cost. You can check out these instructions at Intel Intrinsic's guide webpage. Here they are, sorted by their technologies. SSE ones are those which allow us to work on 4 elements. Modern AVX instructions with 8. AVX 512 with up to 16 elements at the same time. However, they are not supported by all computers and do not support it by ARM architecture devices at all. To be more conscious about your choice, you can check the Steam hardware survey. There you can see how much computers on which Steam is installed support the technologies that you are about to use. You can also sort these instructions by their category, like arithmetic, compare, shift, cast, and many others. Using these instructions is really easy. Imagine we have an array of 4 floats. We can load this data into a single M128 type variable by using load_u_ps, which we can literally decrypt as load unaligned packed singles. We can also set the contents of those variables ourselves by using set function. However, for some reason this function flips the order of elements that you pass in. So you can use the set reversed version of that function and pass elements like you would do intuitively. We can also fill 4 components of a variable with the same value by using set1 variation. After we set our variables, we can perform some basic arithmetic operations like multiplying contents of 2 of them together, maybe dividing by 4, take a minimum between all corresponding components, and then finally store into the initial unaligned array. And remember guys, we operate on 4 elements with just a single instruction. In my personal experience, you could be 3, sometimes 2 times faster. It's worth rewriting performance-critical computations. Many programming languages have bindings for SIMD instructions, so go ahead and check out if your programming language can support them. But for now, let's continue. Imagine that this is our CPU. It's not a secret that CPU may contain multiple cores, which are known as physical cores. The feature of CPUs to have many cores is known as multi-core CPU. Each core is an independent unit which is capable of executing a series of instructions. This series of instructions can be also named as a thread of execution. By default, all programs run on a single thread which is known as a main thread. However, we as programmers can use the power of multi-core CPU to create many of those threads, especially when there is a lot of similar work to do. For example, imagine we have a lot of computations to perform. We can split these computations into 8 parts and tell 8 threads to perform these works. Almost every modern programming language has an ability to manage threads. This includes thread creation, termination, putting it to sleep, and others. By the way, the cost of creating and terminating a thread is in fact very expensive for an operating system. So technically, to create and to terminate thread per work is bad. What we can do instead though is to recreate at the start of the program, 8 threads, which we call worker threads. They will wait for work to appear, and when it happens, 3 worker threads will compete to get and to execute it. When the work is finished, the worker thread will become free and ready to get his next work. This approach is known as a thread pool. Some CPUs have their physical cores split into 2 logical cores, which actually behave like physical ones. This feature is known as hyperthreading. I have no idea how they managed to do so, but bravo Intel. I want to show you an interesting example. Here we have a core with 2 threads associated with it. If that core wants to execute instructions from those threads, it has to switch between them. To do that, it has to suspend one thread, save its state, and load state of a new thread. As you can see, that switch is very expensive, so it's not recommended to create more threads than the number of logical cores on your CPU. This technique won't boost the performance of your program. However, it might save a lot of your time that you possibly can spend waiting for the compilation. The idea is really simple. In a project, we usually have CPP files and header files that are included into them. In fact, the combination of CPP file and all header files included into it is called compilation unit or translation unit. When we hit compile, Mr. Compiler will walk through all translation units, compile them individually into object files, which then pass to linker. They can be linked with some static libraries and built into executable there, which we can then run and play. The most slow part here is the compilation of translation units. To speed it up though, we can create another CPP file to which all of the other files will be included. And tell Mr. Compiler to compile only that file. That way we will be faster not only on the compilation stage, but at the linking stage as well. This tactic is known as unity build, because we literally unite the build of many CPP files into a single one. I read that it has some drawbacks, however I've never actually experienced them myself. Here's an example of how it might look. Now I will show you how I compiled a project that has thousands and thousands lines of code and tens of files. I hit compile, and we're done. I hope you are not tired. Let us energize a little and have a quick run of a few simple tricks. Are you ready? Let's do this. Avoid square root. If you visit the Intrinsics Guide webpage, you can make sure that this operation is slow. It may take up to 40 CPU cycles depending on CPU architecture. For example, imagine we have a vector. From Pythagorean theorem we know that the length of the vector is equal to the square root of the sum of its squared components. Let's say we want to know if its length is less than 5. To get rid of the square root here, we can raise both sides of this inequality to the second power, and we'll still get the correct result of the comparison. Avoid divisions. Divisions are more expensive than multiplications. You can avoid floating point division by 2 with multiplying by half, division by 4 with multiplying by 0.25, division by 10 with multiplying by 0.1, and so on. Also, if you need to divide multiple numbers by the same value, it's better to invert this value once, and then multiply those numbers with this inverted value. Use shifting to divide. We can use shifting to multiply or divide integer numbers by other numbers that are powers of 2. You can shift to the right for division and shift to the left for multiplication. For example, if you need to divide something by 8, 8 is equal to 2 raised to the third power, so you need to shift that number to the right 3 times. Use binary AND to get modulo. Modulo is the remainder of the division of A by B. This technique will also apply only if B is the power of 2. Here you can see the general formula, and let's actually look how can we apply it. Imagine you have value A equal to 21, which is 10101 in binary form, and you want to know the remainder of division by B. Let's say B is 16 and 10000 in binary form. Also, it's equal to 2 to the 4th power. If you subtract 1 from it, you will get 15, the same as 4 ones in binary form. If you now apply binary AND to 21 with 15, you will get 5, and that is the result. Phew, it was really nice run. I hope you liked these easy ones. It's also important to mention that you will really see the effect of these little techniques only if they are used in performance critical sections like functions or code regions that are executed thousands and thousands times per frame. If that's not the case, maybe you should optimize something else? All of the techniques up to the end of this video, which I'll show in a moment, can reduce the amount of work that a GPU should do. They are all based on one or more of the next principles. The less data you send to GPU, the better. The less objects you render, the better. The less you call graphics API to do something, the better. And the last but not least, the more you use the power of GPU computations, the better. The first one is Frustum culling. It is designed to reduce the number of objects that should be rendered. So, imagine that these are all objects that we can possibly render. This is a player. All objects that it can see are highlighted in yellow. It makes no sense to render all other objects, because we will literally waste our time rendering something that we will not see. In 3D world, we extract equations of 6 planes of a frustum formed by camera near and far clipping planes. Same as before, we check if an object is inside a frustum. If so, we render it, otherwise not. Occlusion culling is another technique for culling invisible objects, but in this case it will cull objects that are occluded by other objects. Like the spheres here. They are all occluded by this sphere. It means that if we take a look from this point, in that direction, we will see only that one. I've never actually implemented occlusion culling myself, however reading real-time rendering book will be a good start. Compute shaders are special shaders that you can use to balance the workload of your CPU. They were made specifically for heavy math computations, and so you can use them to speed up calculations of physics, animations, particles, ray tracing, and so on. Compute shaders are really powerful, so consider using them if you need to. When we tell Graphics API to render something on the screen, we make something known as a draw call. When we have a lot of objects in the scene or a lot of characters to print on the screen, we'll probably need to make a lot of draw calls. However, draw calls are really expensive for GPUs. They require the Graphics API to change its internal state to prepare and to render the object, which is really heavy operation. The same thing applies when you want to bind a texture on your object. So next techniques are designed to reduce the number of draw calls and the number of texture bindings. Instancing is a feature of GPUs to render the same mesh multiple times with just one draw call. You tell the GPU which object to render, as well as transformations of target objects that you want to see on the screen, and Graphic API will render these objects there with those transformations. That way we can render a really huge number of similar objects with just a few draw calls. If you have to render a lot of text on the screen or do any other operation which requires frequent texture bindings, you will become very slow soon. So we have to do something to reduce those bindings. And actually there is a straightforward way to do this, is to use Texture Atlas. It is a big texture that holds all other textures, and it's bound just only once per frame. Then we just fetch needed areas from that atlas. Awesome! Also, there is one alternative to texture atlases, which is called texture arrays. Texture arrays hold equally sized textures and can be accessed by an index. Batching is the process of combining the geometry of multiple meshes into a single buffer. In this example, instead of rebinding geometry per character, we bind batched geometry only once. We can also apply a texture using Texture Atlas to have the best from two worlds. I want to thank you for watching this video up to the end. It was really long and I hope it was really helpful, by the way. Please guys, share this video with your friends and with your colleagues to help me spread it. It's really appreciated. Consider hit likes and subscribe. Also, I want to thank all of my patrons for such a generous support. Thanks to my loving wife Kate and to every one of you once again. I wish you the best of luck and I'll see you soon. Goodbye.